Okay, so I hope everybody can hear me.
Yes, yes.
Okay, let's start. So I think all of you are now quite comfortable with correlation and t-tests, as I saw you performing the analyses during the sessions. So now it's time to progress to more complex topics, but more useful topics, namely regression. And today we'll be talking about performing linear as well as logistic regression analyses and interpreting the coefficients that we get. So let me start. Okay, so I think you can see the screen. So I want you to open yesterday's data set. The album sales data set. By now we know what this data set is and what all the variables are. So again, just to recap, adverts stand for thousands of pounds, right? Spent in advertisements. Sales stand for the number of million copies sold of the album. Airplay stands for the number of hours spent on national radio stations. And attract or the attendance ratings are the median attendance ratings that people saw the band as. So yesterday we performed earlier correlation analysis to um, test the association between advertisements and sales. So whether there was any association between advertisements and sales, and we saw that there exists a positive and a significant and a large association or correlation between advertisements and sales. So as the number of as the pounds, as the money spent on advertisements increased, sales also increased. So that is how. But you can also interpret this coefficient as the number of sales increase, the number of advertisement money spent on advertisement also increase. So there is no direction here. Direction here of what predicts what in correlation. In regression, there is a definitive direction. So basically, with the dependent variable being sales, right? So sales is a dependent variable and advertisements will be the independent variable. We can show that advertisements explain sales. So that advertisement predicts sales. So we can conclusively state the prediction. Usually, what needs to be done is that usually we'll need to perform some descriptives, get some descriptives for the data. Excuse. Okay, so basically in linear regression, we are not going to use the sales as a dependent variable and advertisements as an independent variable. If you go back to the PDF which I shared of my PowerPoint presentation of the first session, and if you see which tests are to be used for what type of data, when you have a dependent variable which is continuous and an independent variable which is either continuous or categorical, you will find that we can use linear regression. In the t-tests and the ANOVA, if the dependent variable was continuous and the independent variable was categorical, we could use either t-test or ANOVA. A t-test for 2 groups and ANOVA for 3 groups or more than 2 groups. Linear regression can be used for both categorical independent as well as continuous independent, as I mentioned. Let me show you the power of regression by going to this regression module. Okay, and selecting the linear regression option. Now we'll put the sales variable into the dependent variable box and the adverts into the covariate. So now if you pay attention closely, we have 2 boxes now. So I'm not going to go into what is weighted regression. I'll just explain the covariates and the factors box. So the covariates box includes scale variables, also known as continuous variables or ordinal variables. So both numerical type of data. And factors contain variables which are nominal or categorical. So now you may be wondering, so this icon, of course, in JASP stands for ordinal data, right? So from smallest to highest, so ascending or descending, whatever. So ordinal variables can be thought of as both continuous or categorical. Because if you think about it, as I explained yesterday, ordinal data does not usually have many categories of numbers. So from 0 to 10, right, 11 categories, you can easily represent them as uh, categorical data like frequency. So how many patients were on scale 0, how many were on scale 1, 2, 3, and so on and so forth. Or you can just as easily represent this data, summarize this data as medians and interquartile ranges or means and standard deviation. So that is why you can see that this ordinal input ordinal variables as either covariates or factors. As you get more adept into performing a regression, into performing statistical data analysis in general, you will recognize when ordinal data needs to be put as a covariate or as a numerical type of data, and when ordinal variables need to be put as factor variables. So that just depends on the type of research question, the type of objective that you have, and your expertise on how to deal with data and how to interpret, get meaningful conclusions from data. All right. So adverts is clearly a scale variable, okay, a numerical continuous variable. So we'll put that into covariates. In any case, there is no place to put adverts into factors because it just does not accept scale variables, this box. So the only place you can put it in is the covariates box. All right. So as I mentioned, I will not be speaking about multiple regression in this session. I'll just be speaking about univariate linear regression. However, I will show you what multiple regression looks like. So the power of regression is that you can put more than one variable to explain a dependent variable. Okay, you can put more than one independent variable to explain a single dependent variable. So now if I put airplay as well as attract in all of them, all three of these variables into the covariates box, I have simultaneous comparisons or predictions with the dependent variable. However, these predictions are conditional. The condition is that the other covariates or other factors need to be kept constant at a certain value. So it is a little difficult to understand. I won't be. That is why I'm not going to talk about that today. So I'll just keep a single independent variable, adverts. All right. And now the interpretation of these tables might seem daunting, but don't worry, I will guide you step by step through this table. Okay, so before interpreting the results of linear regression, univariate linear regression. So this is also known as simple linear regression when you have one independent variable, also known as univariate regression, also known as univariable regression. So there are multiple synonyms for this. If you go in the model drop-down menu, you will see certain options which you can put. In univariable regression, there is nothing much to add or modify. Okay. In multiple regression, you can play around with model components. You can add interaction terms, which is subject for another session, not to be talked about today. So basically, for this session, this is not important. In the statistics dropdown, now this is very important because you have various options, test assumptions to get some statistics and so on and so forth. The most basic statistics that we need are, of course, confidence intervals. So that is a must to have. Confidence intervals are a must. So you select this checkbox. Bootstrapping is also a topic for another session. Okay. Now, the essence of regression is actually when you plot raw data points and you plot a best fit line, the distance from those raw data points to the best fit line are what are known as residuals. And you weigh those residuals, and then you calculate some statistics to get your regression coefficients and basically all the entire analysis in a regression. So that is another complex topic. This is again, I'm putting all these topics for another session, but that is because we are going to be short on time for both linear and logistic regression. Basically, here confidence intervals are the only checkbox that I will explain. The another important checkbox is the collinearity diagnostics, but that also comes into play when we have more than one independent variable, and we need to check whether. So there are certain assumptions as well for linear regression. I haven't talked about assumptions. So let's just go to this info for this analysis, and let's talk about the assumptions. So one assumption is that the independent variables, so this independence of residuals, so the independent variables, all the residuals are not correlated with each other. And the multi-collinearity diagnostics that we saw, the collinearity diagnostics, test for this assumption. But that only comes into play when we have more than one independent variable. So the assumptions are continuous response variable. Here the response variable or the dependent variable is continuous, so that assumption is of course met. Linearity and additivity. So the response variables linearly related to all predictors, and the effects of predictors are additive. So again, this should be linearly related to this variable. Again, if you remember, that was another assumption in correlation, Pearson's correlation as well. I talked about independence of residuals. Homoscedasticity is the error variance of each predictor. That should be constant across all values of that predictor. Again, a complex topic. And the normality of residuals. So this assumption is met. This assumption is met because we tested the linearity yesterday in correlation. That is positively linearly related, right? If you remember. Independence of residuals, those are independent. Homoscedasticity, we are going to check that in the using plots, and normality of residuals also we're going to check that using some plots. So that is all for statistics. The main important things that okay. So confidence intervals is the most important checkbox that you need to select in statistics. All right. So before going forward, again, in multiple regression, you have some options. So if you have lots of predictors in multiple regression, for example, you might have heard of genome-wide association studies, so GWAS. Those typically have thousands of predictors for a single mutation or genetic disease. To test all of those genes, you need to perform regression analyses for all of those genes. And here is when you can perform stepwise regression. What is on a stepwise regression? Essentially, we have three methods: forward, backward, and stepwise regression. And you can specify some criteria using this drop-down menu. Again, this is not a topic for today's discussion. And finally, plots. So the important plot that we need to get is this QQ plots of standardized residuals. This will check for normality. And if you remember, I talked about QQ plots during t-tests. And basically, if all of these points fall on a straight line, this is the straight line, and they are very closely knit to each other, falling on the straight line, your data is normally distributed. Of course, as I mentioned, these are outlying points, and outlying points usually tend not to fall on this line because outliers are outliers and they have extreme values. So it's fine if the outliers are, little spread apart from this line. But the important thing to visualize is that these points are uniformly spread on the straight line. They are very close to each other. So the assumption of normality of residuals is met. So one more assumption is met. Okay. Now marginal effects plot. To select this plot, it will just give you a best fit line for univariable regression. Let's wait for this to load. This will essentially be again a best fit line with confidence band. So these are 95% confidence intervals. And this is essentially for univariable regression, the same regression line that we got in yesterday's plot. This is the same graph, but with little less information. We do not get these nice histograms that we got. We do not get correlation coefficients, and we do not get the raw data point scatter. These are called known as rugs. Okay, so these rugs are basically the density. So the more closely these rugs are close to each other, the more data there is. So you see the density is quite high between 0 to 1000. So there is a lot of data between 0 to 1000, but there is sparse data after 1000. So that is how you can interpret these small rug lines. And I think that is all. Now let me finally come to the explanation for these tables. Okay, the first table, that is the model summary. And the only statistic that I want you to concern yourselves with is this R squared underneath in the H1 row. Okay, so the alternative hypothesis ka row, the R square. So this is 33%. So okay. Now what is R squared? R squared is the coefficient of determination, and it explains how much of the variance of the response variable is explained by the predictor variable. I'll repeat that again. This R squared value is a statistic, is known as coefficient of determination, is basically how much of the response or the dependent variable, how much of that variance or variability is explained by the predictor variable. And this is a proportion. This is 33% in this case. Okay. So that means that advertisements explain 33% of the variance in album sales. That is how you can interpret this R squared value. All right. Now the next table, the ANOVA table, analysis of variance table. So this again gives you an overall p-value for the regression. And this is highly significant. This is 10 raised to minus 19. It is very highly significant. And that basically means that this model is significant. So whatever model, so this is known as a regression model. So basically what we have fit is known as a regression model. It's a fancy term, model. Okay. So this model is statistically significant and the p-value is significant. So that is the information that I want you guys to take away from this table. Nothing more at this level. Now the important table, the most important table arguably is the coefficients table. So here, because we selected the 95% confidence interval bands in the statistics drop-down option, we now get nice confidence intervals and the p-value. So the row which I want you to check out is this adverse row underneath the H1 alternative hypothesis, adverse row. So what is this unstandardized column? So this unstandardized is the unstandardized beta coefficient. So how do we interpret beta coefficient? So this is 0.1. So we interpret that for each, so now for each unit increase in sales, so for each unit increase in adverts, the sales increase by 0.1. Okay. So for each unit increase in advertisements, the number of sales increases by 1 unit. So that is how we interpret this. All right. So what is the unit for sales. So what is unit for adverts, first of all? So adverts are, these are pounds in thousand. So 1,000 pounds. So into thousand. This is 10,256 pounds. So basically multiply each of these by 1,000 and you get the number of pounds spent on advertisement. So this is, the number of pounds actually spent divided by 1,000. So let me just write this to make it easier. So for that is how we can interpret. Okay, so what is 1 unit of advertisement? So for each 1,000 pounds spent on advertisements, okay, so the number of sales increases by 0.1 into that. If you remember, it was 1 unit is 1 million sales. So 1 million is 10 lakh. So sales, or 100,000 sales. So that is how you interpret this coefficient. Okay. So if this was 0.5, then it would be, 5 lakh sales. And so on and so forth. So basically you interpret this coefficient. So for each, so this is the statement that you need to keep in mind. So for each unit increase in adverts, each unit, so that is how you interpret this. The number of sales increases by these many. So the beta coefficient unit, so increases by, you insert beta, or let me write unstandardized. And you insert whatever coefficient you have here. So that is how you interpret these coefficients. The p-value is also significant. That means that this is a significant predictor. Okay, so this p-value indicates that this is a significant predictor. So if you have 5 or 6 predictors, whatever p-values are significant, so those are significant predictors for sales, and those which are not significant, those are have insignificant p-values, are of course not significant predictors for the sales. I hope this is clear, and I am going to give you some time if you have to ask any doubts you have right now. So this was linear regression with a continuous independent variable. The next example we are going to discuss is linear regression with a categorical independent variable. Yes, Vidhi.
So if we want to show like a prediction is like a causation only, right?
Yes.
So we will have to have a temporal thing, right? Like the sales would have to be after the advertisements, like there should be a temporal thing present between them, right?
Well, yes, but it is, you would need to conduct a longitudinal study to show temporality. All right. So the type of study is also important to show a temporal relation. A cross-sectional study, if you perform a cross-sectional study, that means you just see it in one point of time. That would not, show a temporal relation. If you perform a longitudinal study, and if you get values at various points of time, you will get causality. So there are multiple criteria to show causality. Temporal association is just one thing. There are multiple criteria. So I think it is given in Park. So there is a certain name for that. I don't remember. So there are some criteria for causality. So the type of study is also important to show causality.
Okay. So JASP assumes all those the basic things are like there.
No, you have to take all those considerations manually. So you have to consider all of those manually, and then based on your subjective judgment, you have to conclude. So
Okay.
causality.
Okay.
Causality is extremely difficult to prove. Association is relatively easier to prove.
Hmm.
Okay. All right. So I think we can progress to the next data set. So I want you to open yesterday's data set. Okay. The t-test and the direct rating activities data set that I asked you to open yesterday. I asked Vidhi to open yesterday. And because I already mentioned, if the dependent variable is continuous and the independent variable is either categorical or continuous, you can use linear regression. So let me show you how you can use linear regression instead of a t-test in this case. I'll also explain why this may be better. Okay, so I hope you have opened this data set. Okay, and now let me just quickly recap what this data set is. So this is a data set of two groups of students. So one group which has been treated, so they have been trained. So DRP is the test which has been administered, the degree of reading power test, and the other scores which students have got in this test. There are two groups, treatment and control group. The treatment group has been trained for this test, and the control group has not been trained. So they have just simply have given this test without training. And we want to find out whether there is a significant difference between the scores between these two groups. So we used a t-test yesterday, and in the first t-test session. Now we'll see how to use linear regression. So I wanted to go to linear regression, same module. And the DRP scale variable needs to be put in the dependent variable box. So the same thing. And now the grouping variable needs to be put in the factors box. So remember that factors or categorical variables or nominal variables, ordinal variables can be put in the factors, and scale variables or ordinal variables can be put in the covariates box. So the interpretation is a bit different. So the only thing which I want to do now, two things which I want to do now, go to statistics, the same things, select confidence intervals, and go to plots and select marginal effects plots with confidence intervals. And after you have done this, you can interpret the R squared in the same way. So the effect of group, so effect of training had 11% effect on the outcome variance, so the score variance. So that is how you interpret R squared. P value 0.03, that means this model is significant, and the coefficients will interpret that now. So I wrote down how to interpret the coefficients for continuous variables. So for each unit increase in the independent continuous variable, the beta coefficient stands as the number of units increased for the dependent variable. So if the beta coefficient is negative, that means for each unit increase in the dependent variable, the dependent variable decreases by those many units. So for negative coefficients, but of course, advertisements was positively related, associated with that. So as adverts increase, sales increase. All right. So how do we interpret? So what is this group and why is this treat? So this, why is the only the treatment group been included? So that is because this is essentially being compared with what is known as the reference class. So regression analysis, if you have two levels of factors, so now this is of course a factor variable, right? The group or categorical variable. And this factor variable has two classes. So treatment class and a control class. So the control class has been taken as a reference class. So a reference class essentially means that it is that level of this factor variable to which all the other levels are being compared to. So for example, if we had, three groups in this case, for example, a control group, a semi-treated group and a fully treated group. So those who were, just given 1 month of training and say those who were given 6 months of training. So partially treated and fully treated. So then we would compare the partially treated with the control group, and we would again get one more row with the 6-month treatment group. And that is again compared with the reference class, in this case, the control group. I'll show you how that looks like in logistic regression. So how to come when we have more than two reference levels or two levels in a factor, how to interpret those. Now, how do we interpret this beta coefficient? So this is basically the mean score compared with the reference class. So it is essentially, in its very essence, a simple difference in means. And I'll also show you I'll also run a t-test on this data and show you this is exactly the same as the mean difference that we get. So this is basically the difference between this group, this level, treatment level, and the reference level, which is a control level. So treatment minus the reference level, and that is the mean difference is shown here. And this confidence interval, of course, is the confidence interval for this coefficient. Okay. And this is a significant p-value. So this predictor variable is significant. In multiple regression, this is not just the simple mean difference. This is this difference is essentially what we call as the estimated marginal mean difference. Again, not a topic for today. Now, if we go to marginal mean, this marginal effects plot, where have we seen this plot? We have seen this plot when we ran a t-test and we got the descriptive plots. This is essentially the mean, and these are the 95% confidence intervals. So let me just add a note to explain this beta coefficient value. So the So this is how you interpret beta coefficients for factor variables. So suppose we had two factors as we constructed an imaginary example. So let's say this was the 1 month treated group, okay, semi-treat group, so 1 month. And let's consider that we had one more group that was trained for 6 months, and suppose that their average, so this coefficient was say 19 in that group. So how do we interpret that? So again, that is again the mean difference with the control group. So the same statement. So the average DRP score in the group full treat, so that is 6 months, is a 19 points higher. So basically, this is the beta coefficient higher than the reference group. Okay. So this is how we interpret the average, the beta coefficients for factor levels. All right. This is basically, as I explained, these points are the means and these are 95% confidence intervals. Now, to show you how this is similar, let me run a t-test quickly. Let me run an independent samples t-test. This data, let's wait for the initialization of this module. And if you remember, this location parameter was essentially the mean difference, and we get the confidence intervals. So if you see this exactly the same, just take the modulus of this, because the groups, JAS sometimes changes the group order. So 9.95, 9.95, 1.09, 1.09, and 18.82, 18.82. So you can see that this is essentially the beta coefficient is essentially the mean difference, and the 95% CI for the coefficient is essentially the mean difference ka beta coefficients. This is only applicable for univariate or simple linear regression. If we have more than one independent variables, then the interpretation changes. Again, I'm not going to go into that, but let me also show you the descriptive plot that we got is the same plot. So this plot and this plot, they are the same. Now, yes, chat. So now if you would like to compare treat to semi-treat, so if we would like to compare treat to semi-treat, we would need to change the reference class. That is a good question. I'll show you how to change the reference class in logistic regression. So I'll show you that, because this new data set will have 3 levels for a single factor. So I'll show you how to do that. I think that was the only message. Okay. Now, let me show you which data set you need to open. So go to data library, go to regression, and I want you to open, go to the variant. And I think this data set, the Titanic data set. Okay. Just open the Titanic data set. I think Pratik is familiar with this data set in the chi-square test. Vidhi, I don't think she was present, but you can open this data set. Okay. So I think you have opened, I hope that you have opened this data set. And let me explain the data set to you. So this is obviously this column indicates the name. So this data set is basically this, the outcome of the passengers on the Titanic. So those who survived and those who did not. So 1 indicates survival and 0 indicates that they died. So passengers on the Titanic, whether they survived or died, and we want to find out what factors contributed to the survival. So P class indicates the passenger class. So first, second, or third class. So which passenger class level were more likely to survive, whether males were more likely to survive or females were more likely to survive, and whether age influenced survival. So all of these can be tested, of course, using multiple regression, multiple logistic regression. But for this example, we are only going to test whether passenger class was, linked to survival. So whether first, second, or third class. So if any one of this class, the they had a better probability of surviving, the passengers on the Titanic. So first, of course, we would get some descriptives. So I'm telling you the flow of this analysis. I'm not going to necessarily do the analysis because it's already 5:50, and this might need a little more explanation. So we would first do descriptives. We would get the frequencies and percentages for the factor categorical variables of class, sex, and survived. The frequencies percentages, we would get the mean standard deviation or the median interquartile range for age. We would also perhaps like to get some contingency 2x2 contingency tables, or not 2x2 necessarily, because class has 3 levels. So we'll do that. So we'll go to frequencies, okay, and we'll go to contingency tables. And we will put survived as columns and class as rows. And we automatically see that, the chi-squared value is extremely high. It is extremely significant. And we would also like to get some percentages. So what would you like to get? Okay. So in column percentages, we see that those who died, so majority of those who died were in third class, 66%. And majority of those who survived were in first class. So if we interpret the row percentages in passengers in first class, so 60% were likely to survived. In second class, 42% survived. Third class, only 19% survived. So now that we have a basic understanding of how our data looks like and what percentages fall into what categories, we now run a regression analysis to predict survival. Now remember that if we have a categorical dependent variable, which is binary. So binary, as you might know, also known as dichotomous. So it has two distinct values, only two values. So yes or no, high or low. So if an event occurred or not, right? So only two values, then you can run a logistic regression. If you have more than two values, you cannot run a logistic regression. And if you have an ordinal dependent variable, you can run what is known as a proportional odds logistic regression. You cannot do that in JASP, but just general information. So just, simply put, if you have a binary or dichotomous dependent variable and you have any type of independent variables, either continuous or categorical, you can run a logistic regression to predict the outcome. So here the outcome is, of course, survival. Okay, so 1 indicates survival, 0 indicates died. Just to repeat myself. So go to regression, go to logistic regression. And this might look very similar to linear regression to you. And it is. So you can put this survival in the dependent variable and the passenger class into the factors. Now you see that we have two classes now. So where's the third class? So we had first class, second class, and third class, right? So where's the first class? Where is this? So this first class has now been taken as a reference class. It was the reference class. The treatment group was the one which we saw. Here, the second and third class are the reference classes, and the first and second are the second and third are the classes which we get our estimates for. Now again, since this is a univariate regression, this is very similar to linear regression. We are not going to play around with the model top-down menu. We will, however, go to statistics and we will select odds ratios, confidence intervals, and underneath the CIs, we want the odds ratio scale for CIs. This is very important because the estimate is the log odds. So this is the logarithm, and odds ratios are nothing but the exponent of these log odds. So it is important to select this checkbox for the odds ratio scale, because the confidence intervals otherwise would be in the log scale. We don't want them in the log scale. We want them in exponent scale, in the odds ratio scale. Okay. Now again, performance metrics, I'm not going to go into that. And in plots, I'm not going to go into ROC plots and anything. I'm just going to go select this conditional estimates plots. And show data point just shows the data points. So that just shows data points. But if you want, you can select that. So these are data points. So yeah. All right. So what did we do? Odds ratios, CIs, and underneath the CIs, the odds ratio scale, and the conditional estimates plot. That is what we did. Now comes the task of interpreting this analysis. So this first table, just look at the p-value. That's it. I'm not going to explain any of the other things. Just look at the p-value. It is significant. It is 0.0000 whatever. So it is 5.84 10 raised to minus 35. So it is highly significant. So this gives the p-value for the entire model. Okay. And now in the coefficients table, this estimate is, as I said, is the log odds. The odds ratio is what we are concerned with, and with the, of course, the 90% confidence intervals and the p-values. All right. So basically, this p-value, these p-values indicate whether the difference in the odds of survival were significant between this class and the reference class. So between the first and second class, there was significant difference in survival, and even between third and first class, as we see with the p-values. So that is how we interpret the p-values. So to repeat, the p-values for a distinct level of a factor, so second level and third level, these give the significance of the probability of survival between this class and the reference class. So both of these are significant. That means there is significant difference between first and second class in terms of survival, and there is significant difference between first and third class in terms of survival. So both of these are significant. All right. Now comes the time to interpret odds ratios. So an odds ratio of 0.5. So before interpreting this, let me tell you the range of an odds ratio. So an odds ratio of 1 is the null value. Okay, an odds ratio of 1 is a null value, similar to what we discussed yesterday. A correlation coefficient of 0 is the null value, right? Similar to that. So because this is a ratio, it is a numerator divided by denominator. So if both are the same, both of the odds are the same, that will of course mean that, say, 56 by 56 is 1, right? So an odds ratio of 1 is a null value. An odds ratio less than 1, so if it ranges from 0 to 1, that means the odds of the outcome are lower. And if it is more than 1, that means the odds of the outcome are higher. Okay. So this 0.5, so remember that the outcome is survival. So the odds of survival of passengers in the second class was only 0.5 times the odds of odds of survival in the reference class. So let me write this down. Okay. So interpretation of this odds ratio. So this is of course, a lower odds. So 0.5 is, half the odds, right? So it is a lower odds. And you can of course report the CI for the odds. So remember that if the CI crosses 1, which is the null value, so if any confidence interval range crosses the null value, that means the result will not be significant. So if this would have crossed 1, that means that the result would not have been significant. Okay. Yes, Pratik.
For the first class, which is the intercept class, is the odds ratio is 1.5.
No, no,
So
that is not the reference class, not the intercept. The
okay, okay.
intercept is just without any independent variable. So just the dependent variable. So consider, so if you imagine a Cartesian, system with an x axis and a y axis. So in a linear model, you would say that a line has, what y is equal to say bx plus c, okay, where c is the intercept. So the, regression, it is interesting because so you saw the regression line, right? So that can be represented as an equation, as a linear equation. So y is equal to bx plus c is the equation for a straight line, where b indicates the slope. And it is interesting because this slope is actually the beta coefficient that we saw. All right. C is the intercept. C is this intercept. And of course, y and x are those specific, variables. So for logistic regression, we only have a binary outcome. So there is what is known as a transformation. So logit transformation for the probability. So, that is a little complex topic. So I won't go into that. So basically in logistic regression, you convert the outcome into a linear response using the logit link function. Then you interpret that. So this is the, when you convert that, you get these log estimates. So that is why we see numbers. But, enough. So, okay, let me present this equation in the form of what we see. So this estimate is minus 0.183x plus c is 0.4. So that is how we would, actually write this equation. But this is difficult to understand when it comes to logistic regression, because this is on a log response scale. It is easier to understand in linear regression. Okay, makes sense. So ideally, the intercept is of no use for our interpretation. Yes, essentially. So just when we consider what is a significant predictor and what is not, it is not, not of much use. Yes, that is the essence. All right. So, okay, now let me report the odds ratio for passenger class number 3 or third class. So the odds of survival, very similar, interpretation. So the odds for survival for passengers in the third class was 0.16 times that of the odds of survival or in the first class. So remember, it is always with respect to the reference class. Okay. So it is always in with respect to the reference class. In this case, it's the first class. Now, the question that Pratik raised, so what if we want to compare between third and second class? That is essentially what the question which was raised. So how to change the reference levels? That means essentially we are going to change the reference level. So we do that by going to the data editor. Okay, click on this P class, and now we'll rearrange this. Okay, select the second thing and move this upwards. So now this is the, essentially the first, second, and third level. So now the second, this second class will hopefully act as the reference class. I'm not sure whether this update of JASP has changed this, but the last update, this worked perfectly. So the second is the first, the second, first, and third. So these are the levels now. And by moving this second class essentially upwards, we have changed the reference level to the second class now. So let's see. Great. So now you see that the reference class is now second class. And this is essentially now a comparison between first and second class and third and second class. So an odds ratio of this third class. So let me now, delete this and let me interpret between the second and third class. So the odds of survival So that is how we now interpret this difference. And the same goes for linear regression. If we had, three, the control, semi-treated group and treated group. If you wanted to compare semi-treat and treat, fully treated group, then we would of course reorder the factor levels. The semi-treat would now, we would change that by reordering, just like I showed you, by reordering the semi-treat as the, reference class by shifting it up. And we would essentially interpret the odds ratio like so. Now, just, to nitpick, it is oftentimes very hard to interpret, or it is oftentimes not very intuitive to interpret odds ratios between 0 to 1. So it is good if we get, odds ratios more than 1. So let me, now put third class as the reference group. And now, because the odds of survival in passengers in the third class were the lowest, now this reference class would entirely change the ratios. So now they would be more than 1. Now you see 6.2 and 3.09. So this is now very nice to interpret. You can also do that by dividing those odds ratios by 1. So if you had, say, the first class, so this was what we had initially. If you had divided so if this was a denominator, so 1 over 0.16, you would get actually the odds ratio if the third class was the reference class. So that is how it is. But now let's put this back where it was, and now let's interpret odds ratios, because this is easier to interpret. Okay, so now look at how easy it is to interpret. So the odds of so they were 3 times more likely to survive. So this is very easy to and very intuitive, right? This is more intuitive. So second class passengers were 3 times more likely to survive than those in the third class. and first class passengers were almost 6 times more likely to survive. So this is very intuitive. And we can also put this into a percentage value. So 3.09 minus the null value of 1. So that is 2.09, right? So, or so that is how we interpret odd ratios now. So in percentages this time. So 3.09 minus the null value of 1, that would be 2.09, and 2.09 into 100. So we get a percentage. So 209%. So, right. So that is how we interpret odds ratios. And okay, now to, interpret this conditional estimates plot. So this is just an estimates plot for univariate analysis. So this essentially is a probability of survival. So first class were, the probability of survival was the highest in passengers in the first class, followed by second class, and the least probability was that of passengers in the third class. So that is how it is a very nice visual representation of probability of survivals. So I think it's almost 6:10, and okay, let me now show you with a continuous predictor variable, the last example. So I will now put age as a covariate, as a continuous predictor variable, and see and interpret now the odds ratio. So by looking at the conditional estimates plot, we see as age increases, probability of survival decreases. Okay. And is this result significant? No, it is not. So this result is not significant, is 0.09, but and you see, okay, so this confidence interval has touched the null value of 1, so it is not significant, and we can this is reflected by the p-value. Okay, so let's interpret for a continuous variable, age. So the odds of survival of passengers, so let's interpret it in a minute. So for each unit increase in a continuous independent variable, the odds of survival increased by 0.99. So essentially, increased by 0.99, that means it decreased, right? If you want to say they decreased, then you would say decreased, and you would divide 1 by 0.99. So whatever the value which comes, 1 divided by 0.99, you would write that 1.0 something, whatever. So the same, you interpret this in the same way as linear regression, but this is just an odds ratio. So this is now interpreted for each year for each year that the passengers were older, their odds of survival increased by 0, or it decreased by 1 over 0.99. So that is how you interpret odds ratio for a continuous independent variable. So I will now open the channel for questions. So if any of you have any questions, you can raise your hand. Otherwise, we can call it a day. Understood. Great. I think you were looking for multiple regression. Sorry to disappoint you, Pratik. And Vidhi, I hope you were able to follow through with,
Yes,
because
completely.
it is oftentimes difficult to follow. Yeah, it is also oftentimes very
Yeah,
difficult
yeah.
to follow regression analysis, especially logistic regression and how to interpret odd ratios. But I hope this was helpful.
Yes. Very much.
Okay.
We'll need a lot
Uh,
of practice though.
yeah, and I did not, ask you to do this by yourselves, because in the next session I'll ask you to share your screens and perform the analysis.
Okay. Yeah.
Okay, I believe Pratik wanted to have a word with me.
Yeah. So this is basically regarding one of the projects that we were undertaking. Uh, I mean, I was trying to find the sample size for it, and what we were mainly doing was that we were taking patient data of these thalassemia patients, and we were comparing. We were doing a retrospective analysis of the last 5 years of their cardiac MRIs and their compliance in the last 5 years, and thereby comparing the amount of days or weeks that they might have missed their
Okay.
medications to their cardiac iron load in their MRI.
So how is that measured? Iron load.
Iron load was measured. There was a value in the T2 MRI which showed their cardiac iron load.
So was that a value a number or not?
It was a number. Yes.
And is there a cutoff value for that? Or no, it is
Uh,
just a continuous
it is just a continuous variable.
variable.
It is just a continuous variable.
Okay. And for the compliance, you have only two groups, right? So so no compliance or low compliance and fully compliant, I'm assuming.
Right.
So why did you want to do proportions? It would be a difference in means, right?
Uh, so for the compliance also, I mean, both of these groups of low compliance and fully compliant, we were kind of trying to do, trying to make those also as numerical variables, as in we'll be comparing someone with uh, 1 week less compliance to someone with 5 weeks less compliance and all, like something like that. Does that make
How
sense?
do you define compliance? How are you defining compliance?
Um, so we're basically taking a baseline of them being completely adherent to their regimen, and someone who's not compliant will miss a few doses, and these few doses may range from a few days of missing
Okay.
to weeks or months of missing, whatever.
Okay. So hmm.
So
So basically
so
what you want, so basically the research question is that patients who were less compliant on taking iron had lower iron deposition on cardiac MRI.
no, less compliant had a greater iron deposition. Less compliant on this thing, no, on medications that will remove the iron deposition.
On iron?
Basically, less compliant on iron chelators, right?
Acha,
So
chelators. Acha, you are saying
yeah,
acha, chelators. Okay.
right,
Okay.
right, right.
Acha, in thalassemia patients. Okay, I got it.
हाँ
ठीक है.
ठीक, yeah.
Fine. ठीक है. Okay.
तो इसके लिए वही सैंपल साइज के लिए आई रियली डिडंट नो हाउ टू गो अबाउट इट. आई ट्राइड डूइंग इट विद बाय ओपनिंग ऑल ऑफ योर नोट्स. तो थोड़ा कंफ्यूजन हो रहा था वही कि हाउ शुड आई मीन when we took a reference incidence of the population, so in a few researches we found that about 0.3% or about 30% of people are non-compliant out of the entire population. So now how to go about it, finding a population plus
No,
also,
I think
yeah,
so. Basically, what you need to do is that, so you state your primary objective very clearly, and
acha,
I think it would be your primary objective would be to compare the iron deposition on cardiac MRI between these two groups of patients, right?
Um, what if we keep it I mean, we don't keep it as two separate groups. We keep it as to compare the ion deposition on MRI on the degree of compliance of those individuals.
So
Uh,
that degree, how do you define that degree? I mean, you define the degree, but how would the data look like? Is what I'm asking.
right, right.
So
Hmm.
would it be, 1 week? So 1, 2, 3, 4, would it be numbers? So
Yes,
of,
yes, yes.
less compliance. So 1 week, 2 week, 3 weeks. So it would be 1, 2, 3, 4, and whatever, so on and so forth till 48,
Yes,
50, whatever.
yes, this is what we were planning.
Acha. So then you would want to use a regression, linear regression for this.
Right, right. But sample size के लिए फिर how do we do that? Sample
So you
size
can
calculation
calculate,
में डाल.
yeah, regression के लिए sample size is easy. Is there? I don't think there is any other study which has been done like this. Is there?
No, there isn't.
There is.
No, there isn't. There isn't.
There isn't. Okay. So there is a sample size calculation for linear regression for a continuous variable, and okay. So I think that is why you were asking for a multiple regression, is it?
No, no, वो तो बस ऐसे in general.
So I think this study would need a
multiple regression. Acha.
multiple regression, adjusting for other factors which can lead to increased or decreased deposition on cardiac MRI of iron. So
Okay.
okay. So putting into simple terms, we want to find out, of course, whether a higher, decreased compliance would lead to increased deposition of iron.
Perfect.
And yes, so that is what we want to find out, and we want to adjust for other factors which would lead. So what are other factors which might distort the result? So which other factors can lead to increase or decrease deposition of iron in cardiac MRI? So that is what you need to find out. And if you have that data available, we need to put those variables into the model, regression model, so that those do not, confound the analysis, basically.
Right.
So adjusting for, what we call as confounders. So might know this term. So adjusting for confounders.
Right.
So here is when. So that is why I thought you might ask for multiple regression.
Yeah, I didn't realize it
Session,
initially
because
that
this
I would.
will be needed for this analysis.
Yeah.
And okay, so yeah, and so if there isn't any other study, we would use probably say a small to medium effect size. So how many cases do you think you have in these 5 years?
Okay, in these 5 years, a total of we have around 120 to 130 cases that come in all these 5 years.
How many? I did not catch your last.
120 to 130.
To 1,000?
No, 120 to 150 approximately. That's all. Yeah.
So instead of formally calculating a sample size, I would, since this is a retrospective study design, you can define that we have included all of the patients during these 5 years. And then if we want, we can perform a power analysis afterwards, because this is a retrospective study. This is not a prospective study. So, formal calculation, you can get away without a calculation. So include all of the patients in that defined time period.
Right.
And after you include all of those patients, we can calculate power afterwards to run this regression analysis.
Right, makes sense.
So if we get more than 80% power, then it is good. If we do not, because if I tell you that, okay, so my calculation has included 250 patients, that would not be feasible. That you would just collect whatever 150 patients you had. So instead of for calculating the sample size right now, it would be more appropriate to calculate power after that. And usually 150 is honestly, it is so might be sufficient enough. 150 is quite sufficient to run a regression with 3 or 4 variables. So multiple regression with 3 or 4
Right.
So it is enough.
I mean, the
So I think,
total number of people who are who will be present for these 5 years are 150, but we would be able to calculate probably a maximum of 100 is what I feel. I mean, take data from a maximum of 100, taking into
ठीक है ना,
consideration that 50-50 go here and there.
ठीक है ना. So that is fine. You calculate. So you take whatever data you can. You take whatever data you can, and we'll calculate power for that later on.
अच्छा,
And
ठीक है.
yeah, and let me tell you completely honestly. Now, thoda sa you need to, you might need to, if, for example, running a very hard and fast strict regression, a perfect regression with 3 or 4 variables as your primary objective, you need to calculate power, and it comes to be 70 or 60%. It is not usually acceptable. So in that case, we can, get away with using a very a simpler primary objective to fulfill our our sample size limitation, and use this regression as a secondary objective. So that is how, because if you submit this to a good journal, right? So the referees or reviewers will ask, primary objective ke liye, you have included so many patients, but you have not included power, or you have included power analysis and it is not more than 80%. So what is the basis of validity for your results and whatever? So there are multiple methods to get around this problem, but I think we'll cross that bridge when you come to it. For now, I think you collect as much data as you can, because it's a retrospective study. I understand that logistic reasons are there for which you might need more manpower to calculate, to enter data and so on and so forth. But I would still suggest that include all of the patients in that time period, and let's calculate power afterwards.
Okay. Makes sense.
Yeah.
So mainly, I mean, for the ethics file, I would want to convince them as to whatever I'm doing. So if I take an average of that, I'll be collecting 100 patients' data. Then for the power analysis, what tool do I use? And with an average, I mean, we already have the data.
Basically, we'll do power.
So we basically started collecting even before getting an ethics approval.
Yeah.
So we have around 70 patients data already, and we are assuming we'll collect 20-30 more.
Okay.
So that's all. So we have
just for the ethics, you need a calculation, is it?
Yes, that's all. Yeah.
Okay. So just wait a second.
Right. Thank you so much, man.
Just don't leave this meeting. I'll just just wait a second.
Yeah.
So for just for the ISC filing, I'll give you the power for 100 patients, and so it would be for a regression with only one predictor. That would be your this thing. Compliance.
Right.
And with a medium effect size. So I'll give you a medium effect size, Cohen's F square of 0.15. And what is the justification for using a medium effect size? there is no prior study from which we calculate an effect size, right? There is no prior study on this topic. So we assume that we would get a medium effect size, and for that, the power is so and so.
Okay.
So it's 96 point, so it's 97%. Your power will be 97%.
Okay. 97. Okay. Yeah.
And
Okay.
and let me give you a power curve directly, actually.
Hmm.
You can, copy paste that power curve figure into your ISC filing only. So
Right. I can't see. Are you trying to share your screen?
no, I'm not.
Yeah.
I'm
Okay.
not trying to share.
Yeah.
I'm just so I'll share this with you. We can end this
Okay.
meeting right now.
Right.
And and I'll share this with you in 1 or 2 minutes. So I'll just download the power curve and share this with you. So yeah, I think any other questions?
That's all. Thank you so much.
Okay, no problem then, Pratik and Vidhi. Nice to have you again, and hope to see you in the next sessions.
Yes.
I'll let you know when we have them.
Yes. Thank you so much.
Okay,
Okay.
great.
Also, there's just one more thing. I mean, there are a lot, as I discussed with you before, there were a few people in our group also who wanted to have these sessions with you. So maybe after this, we can plan out whatever is possible.
Yeah, we can. Actually, my rural posting is going on, so it
Okay.
is a little, so it's a little hectic for me, at least till 25th of April. So 20 more days, so 15 more
Right.
days.
Right.
So after that, I think we can have
Okay.
sessions.
Okay. Perfect.
All right then.
Thank you.
Yes. See you guys. Have a nice
Bye.
day. Bye bye.